So Chapter 7 looks at the terrestrial planets, those inner planets, those planets that were formed on this side of the frost line, as we talked about in Chapter 6. In general, the terrestrial planets all have a very similar structure, and they kind of look like this, where the gray area is the core, and it's got the densest material, and then kind of that kind of orange-colored region is what we call the mantle, and the mantle actually has kind of a lower part that's little ooey gooey, and then the upper part of the mantle up here that is solidified, and actually then we have the peach area, which is called the crust, and the top part of the mantle and the crust make up what we call the lithosphere. So here in a minute, when we talk about plate tectonics, we're going to talk about the lithosphere kind of floating around on the liquid part of the upper mantle. But the densest material is in the core, and the lightest material is in the crust. So just kind of a bird's eye view of all of the terrestrial planets from the largest to the smallest. And you can see what I mean by they have similar structures with the core, the mantle, the crust, and they have a lithosphere. So we have second in size to the Earth is Venus. And then after Venus, we have Mars. And you can kind of notice the relative size there. And then we have Mercury. And check out the Mercury's core. Wow, that's crazy. And then we'll go ahead, and I know it's not a planet, but Earth's moon, we'll go ahead and throw that up, because as far as being, it is very rocky. Instead of, in the next chapter, we're going to talk about the planets that are gaseous. So, relatively speaking, you can see how all of the planets have those same kind of 3 or 4 components, including the lithosphere. So, for all of the planets, the core is the densest material. And the reason that it went down that way is early on in the formation of the planets, they were very, what I say, ooey gooey. And the ooey gooiness, or the moltenness, allowed migration, allowed material to sink, the heavy material to sink, and the lighter material to rise. So because of gravity, the dense material sank to the core, and the lighter material rose up to the crust. And this generally is called planetary differentiation. So it's differentiating based upon density. So the dense things sink, and the less dense things, or the buoyant things, rise with lower density. And this is kind of similar to salad dressing. If you have like some sort of oil and water, or oil, water, and vinegar salad dressing, when you shake it up, you can get the oil and water to mix. But when you let it set, the water is more dense and will sink, and the oil will rise. So planetary differentiation is like Italian salad dressing settling. So the lithosphere. I mentioned that the lithosphere is actually what gives us our plate tectonics, and we'll talk about that shortly in this chapter. But the Earth's crust is segmented into what we call plates, and actually it's not just the crust, but it's the bottom part. The top part of the mantle, the crust, and the top part of the mantle is called the lithosphere, and that's what's going to float around. So one of the things about rocks, we usually think of rocks as not very, what we say, malleable rocks. You can't kind of bend, and you can't reshape a rock. But if over time, you could reshape a rock. Rocks will deform or stretch if force is applied slowly over time. And actually, it's that applying force slowly over time that kind of gave our terrestrial planets their sphericalness. But another thing about rocks is if you apply a force but not slowly and over time, your rock will break. Okay, very much like silly putty. Silly putty you can stretch as long as you take your time. But if you take care of that silly putty and you apply a force quickly, that silly putty is going to break. And so rocks do the same thing. Rocks are like silly putty. So plate tectonics, you've probably learned about plate tectonics in maybe an earth course, geological, earth science course. And if I go back to the mantle here that has actually a liquid part of the mantle here is between the core and the crust. And the upper part of the mantle then is rigid and attached to the crust in this part of the lithosphere. But we'll talk more about, in the next slide actually, we'll talk more about this, but the Earth's core, in like all planets, the Earth's core is the hottest part of the Earth. Okay, you think you're having a hot day, well just picture yourself in the center of the Earth, and temperatures do increase as you go towards the Earth's center. So the Earth is cooling off, and so what happens is kind of much like a lava lamp. So if you picture a lava lamp and you turn on the heating element at the bottom of basically you have two liquids in your lava lamp and they don't dissolve in each other. They are immiscible. And so you apply a heat, probably with a light bulb, and what happens is the material near that light bulb gets warm, and as it gets warm it expands, and as it expands it becomes less dense than its surrounding, and as it becomes less dense then it wants to rise. And so you see that material rise in your lava lamp. Much the same way mantle in the Earth's interior will rise because of heat. Let me see if I can go ahead and just highlight a few things. So picture heat. I'll just put I'll put E for energy, thermal energy, heat. How's that? And so this is turning on your light bulb, and can you see that we have material here going up? Okay, we have material here going up. That would be like your lava lamp material floating. And then just like your lava lamp, at some point, or on the way up, I guess I should say, that material starts to cool, and it will get to the top of your lava lamp, and it will be cool, and then it will want to sink back down. And so here the material cools up here, okay, and we'll talk about kind of giving off its thermal energy, and then it will, after it cools, it will want to sink back down. Okay, actually, as I have it drawn here, we have two separate what we call convection cells. Okay, and so the material rises, chiller heats because of the Earth's core. It rises and expands, or I should say expands and then rises. And as it rises, it cools to the point of being dense again, and it falls back down, and it can start all over again. One of the things I think is interesting is how long it takes for the material to go one cycle is about 100 million years. Isn't that interesting? Okay, so remember we're going to picture E, or heat, E for energy, specifically thermal energy in the Earth's core here. So that energy can get ultimately out by three different ways, and actually heat in general is transferred one of three ways. It can be via convection, and actually convection is what I mentioned, the convection cells, that liquid part of the mantle warming up near the Earth's core and expanding and rising, and then cooling and then sinking back down. So we have two convection cells right there. The next way that thermal energy or heat is transferred outward from the Earth's core is via what we call conduction. And conduction is kind of like the molecule to molecule to molecule, or butt to butt to butt. And for instance, conduction is why when you're stirring hot water on your stove, if you use a metal spoon, conduction is what will get you in most cases. The heat will travel up your spoon, molecule to molecule to molecule. That's conduction. So conduction to cool the Earth off actually kind of happens here in the lithosphere. Okay, right here, and I kind of labeled those B. The last way that thermal energy can be transferred is via radiation. We spent a fair bit of time talking about electromagnetic radiation, and one form of radiation that has a relatively long wavelength, low energy compared to gamma rays and X-rays, we said was infrared radiation. And actually that's what we have here, infrared radiation going outward from the Earth. Okay. So remember, radiation can travel in a vacuum. It needs no material, it needs no molecules, that sort of thing. So there is the Earth cooling off. So if we kind of look again at size, I'll put these up here, largest to smallest. Earth is the largest, followed by Venus, followed by Mars, Mercury, and we'll go ahead and throw up the moon there. Okay. When we talk about plate tectonics coming up, okay, we're going to see that the smaller objects cooled more quickly, and that would make sense to you, I'm sure. So if an object cools, if a planet cools or if a moon cools, then it no longer has those that liquid part to its mantle, and you can no longer have plate tectonics. And again, I bet you're familiar with it, but we'll talk more about it in Chapter 7 here. Plate tectonics are what make a planet or a moon geologically active. So in that sense, actually there is no active plate tectonic movement on the moon or Mercury, because those objects, although they were ooey gooey, part of their mantle was ooey gooey early on, they cooled off, and that's no longer the case. So they're geologically dead. The Earth is geologically active. Okay, plate tectonics, by the way, are why we have our earthquakes. Plate tectonics are associated with faults, divisions between major plates. Plate tectonics, to me, I guess just because it's geologically active more, is when we have our volcanoes. That's because we would consider that a geological activity. Venus is, we believe, geologically active, okay, because of its size. Venus, again, is warm enough that it hasn't cooled down yet to harden, so it doesn't have any geological activity. Mars, the jury is still out, as far as I know. I did a little bit of research just online, and I could not find a clear cut whether Mars has some liquid part to its mantle still.